Okay, in this video, we'll have a few sample problems here dealing with the conservation of mass principles. Um, so I guess we'll discuss here qualitatively the idea as we go along, and then quantitatively go through the analysis involved. This first video here, and again we have two lectures on it, so we're going to have two supplemental videos to those lectures. And so this first one will just be a bunch of sample problems that's main focus is on the unsteady systems, or that time-changing part of the continuity equation. We'll see it here in the early stages of this first solution, what we mean by the continuity equation. But there's an unsteady part, or there's a time derivative part, a time-changing part of the continuity equation. And then there's a mass flux term in the conservation of mass. But let's focus just on this first problem here. And again, all of these problems will be dealing with that unsteady term as the main focus. I think we'll see the mass flux term come into play in one of these problems. But then the next supplemental video to the next lecture will focus more on the mass flux terms. So this is 511 from your book, this first problem, and this just a paragraph, no diagram here. We just have we want to empty an aquarium that's filled with water into a bucket. So we're going from a rectangularly shaped aquarium to a circular cylindrical bucket, and we know, our first conservation of mass principle showing up here, that as the aquarium water level lowers, as the amount of material or mass inside the aquarium decreases, it has to increase somewhere else. That needs to go somewhere else, and that's going into a bucket in this case. If you were pumping the aquarium water down a drain, well, that mass would then go into the pipes for a while, and then that mass would then go into some reservoir somewhere downstream in the water system. But we're given that the bucket, you can maybe measure the water level in the bucket is increasing at 4 inches per minute. So what is the associated decrease in the aquarium water level height? So that's our question. All right, so I've rewritten it here. An aquarium which is originally filled with water is being pumped into a cylindrical bucket, circular cylindrical bucket. Determine the rate of the decreasing water level in the aquarium if the water level in the bucket is increasing at a given rate, 4 inches per minute. So here's my diagram. Again, none is given. So have to determine what the diagram should be yourself. And so I just have a rectangularly shaped object here. I'm calling the aquarium, and a circularly shaped cylindrical shape here called the bucket. All of the heights are given, or as given in the problem statement, are drawn on here, where I've also labeled them with letters or symbols so that we can keep things general. So the original, the total height, length, width, and height of the aquarium are given, and then the diameter of our cylindrical bucket is also given, and I've given those letters. And I've also then in blue shown HB and HA. So this is the height, the aquarium water level height at any instant in time, and this is the bucket water level height in any instant in time, right? So those are variable. HA and HB are variables in time. The H, L, and W are fixed, and so is the D. Those are fixed geometrical constraints on the system. And then we have the piping system and the pump involved, right? Just drawn on here. Well, at this part, you wouldn't know, at this part in the solution process, we wouldn't have this control volume drawn on here that comes during the solution. But with the pre-drawn diagram here, everything is shown to you at once. But again, our goal here is to find the change in the aquarium water level height with time, given the bucket, change in the bucket water level height with time at 4 inches per minute. Okay, so on to the solution. First step here is to draw a control volume. And for this one, I think it makes sense to include all of the water in the system. We can draw our dashed line around all of the water involved in the system, knowing that that's going to then change its shape through time. The control volume will change in time as the aquarium water level drops and the bucket water level rises, right? The shape of the control volume will change. But that's not a problem, because with a moving control volume, all we have to do is make sure that we account for any flow across the control surface, even when it's moving, that is a relative flow a relative flow of fluid across the control surface. So in all of these cases, there's, as we allow the system to move with the water level height, there is no flow. That's why we're doing it, is that there's no flow across the control surface anywhere. Right? So if we left it fixed, a fixed control volume, and let the water level drop, and kept this one fixed and let the water level rise, right, there's going to be either water flowing across the control surface or air. If it really looks like this, there's going to be something filling this space as the water level drops, and that's likely going to be air, and then we'd have to account for that air in our conservation of mass analysis here. But and over here, I don't know if you fixed it at the total height of the bucket, right? Well, then there would be water flowing out, air moving out as the water flows in. But we choose it to always be at any instant in time where the water levels are, and therefore there's no flow across the control volume at any instant in time. So that allows us to draw out write out the entire continuity equation, saying that the total change in mass with time needs to be 0 for, oops, that's not the right, this needs to be a total derivative. So the total change in mass with time for the entire system, or the entire control mass, needs to be 0. And this is the fundamental law. If you follow a bunch of particles, choose what they are, and follow them along, their mass can't change for a fluid system. Okay, but we think about things in an Eulerian frame, and so we write things out in terms of their spatial and time components here, in their coordinates in space and time. And so that means we have to do this breakdown between the change in the mass within a fixed control volume, right? So we're choosing an Eulerian approach, looking at just a control volume. I guess it's not completely fixed in this case, but the change in mass within that control volume must be balanced, therefore, by fluxes through the surfaces of that control volume. And if there's no fluxes of mass through the control surface, then there must be no change in mass within the control volume itself, right? And so that makes sense, that if we encapsulate all of the water within our control volume, and then don't let the water leave the control volume, the total mass must be conserved. Well, I've written here in general, we say there's no flux of mass through the control surface. I mean, that just comes from our choice of what the control volume is. We'll generally leave this one non-zero, let's say, because the volume looks like it's going to be changing, right? So as we're moving up and down, the volume of our control volume changes, right? It's an incompressible fluid, so we're going to quickly be able to take this density out. But the volume itself, in a general sense, is changing here, or at least shifting around. But what will end up happening, the amount of the control volume in the aquarium decreases, the amount of volume in our bucket will increase at an equal rate. So equal and opposite in this case. So by just focusing on that time, that unsteady term, this is our equation. 0 must equal the time rate of change of the mass within the control volume, where the mass within the control volume is the accumulation, or the integral, of the density of the flow times little infinitesimally small volume elements. Well, our density is constant everywhere. So because we're dealing with incompressible fluid, water, so we can pull that not only out of the integral because it's constant within the control volume itself, but we can also pull it out of the time derivative because it's not going to change with time either. So that's why density has been pulled out of everything. Well, then we just have time rates of change of the integral of little volume elements over the entire control volume, right? Well, the integral of dV over the volume is just the volume itself, but with our system, we need to break it up into the two parts of the aquarium and the bucket, right? So we have pulled the density out. Now we just have the time rate of change of just the volume of the aquarium, that part, plus the time rate of change of the volume of the bucket. And so those must balance each other and equal out to 0. So as the aquarium volume, the amount of volume of water in the aquarium decreases and this goes down, right? So this is going to be negative. That must be balanced in an equal and opposite way of the volume increase in the bucket. All right, so this is going to be positive, this one's negative, and they must be equal and opposite to make their conservation of mass hold true. Okay, so what are all these things? Well, our volume of the aquarium is just the length times the width times the height, but the length and the width are set. So as the water level on a rectangular box decreases, the length and width don't change, but the height is changing in time. So that's the only thing that stays in the time derivative. I've canceled out density here because it's just equals 0, so that's not going to play a role. And the change in the volume of the bucket, right? So this is going to be circular cross sections that don't change in time. So we have pi d squared over 4 is just the area of those circles. But then for the volume, we just need to multiply by the height, and that does change in time. So the height of the bucket does change in time. Right? So we pull everything that's constant out, and we're just left with these. This is our unknown, and this is a known quantity given in the problem statement. So this is what we're looking for. We solve for this. This is the change in the height of the aquarium water level with time. Pull everything else to the other side of the equation, noting quickly that we're going to get a negative sign, which we expect to see because this is a positive quantity as the bucket level, water level increases in time. And we just plug everything in. I don't think there's anything tricky here. We're just plugging in the geometries and that this was given as 4 inches per minute. And we find that the aquarium water level is now decreasing at ½ an inch per minute. That's kind of a small pump, I guess, we got on here, and a slow rate of decrease. Although I don't have much experience with draining aquariums, I do have experience with draining rotating tanks, as I've discussed in the past, and we have even just a siphon system can probably go a bit faster than this. So this will all kind of depend on how big your pipes are or your tubing that you use to drain these systems, and then the power of your pump. And if you're using siphon, you can just use you don't even need to use a pump. You can just use elevation changes to do that work for you. But all right, so let's move on to another example. This sample problem is 512, but not from the book we're using this semester, but from a previous edition in the book, and it doesn't show up in the new edition of the book, but thought it was a nice problem to do now. I'm just finding it here. Okay. So it's down here, 512. We have another, another container here, a cylindrical container, and it's originally filled with gasoline, let's say, and we're trying to flush it out using water. So we inject water here through an inlet, and that's going to push the gasoline out. And so the question here is, what is the time rate of change of the mass of the gasoline contained in the tank? So as the water displaces the gasoline at a rate, let's see, 100 liters per hour, we should be able to determine what the mass of the gasoline, what its time rate of change for the mass of gasoline in the tank is. Okay, so again, this is an unsteady part, but I think this is the part where, depending on how we look at the system, we do have the flux terms showing up here, and I'll talk about how we're going to be very rigorous with this, right? So overly rigorous to kind of prove something general about, I guess, to prove for this system something that we, in the book is derived generally for all systems dealing with incompressible fluids. But so I've reworded the problem statement here that water enters a cylindrical tank, forces gasoline out. Let's determine the time rate of change of the mass in the tank, noting that the specific gravity of gasoline is 0.68. So that's why it's living above our water in this system, because it's lighter. And we're given that the volumetric flow rate is 100 liters per second. Is a, that I think was 100 liters per hour, and that converts to 100 centimeters cubed per second. Yep. Okay. So, again, all these problems, it's a good idea to just start with the full continuity equation. Again, this is the total mass of a system, or of a control mass with time, must equal 0, broken down into its time rate of change within a control volume plus the fluxes through that surface, through the control surface. It's actually the net flow out of the surface, such that if we have something changing in the mass of the mass within the control volume changing with time in a positive way, right? So increasing, it must mean that we have a mass entering the system with a net negative mass outflow, right? So if this is increasing, the mass within the control volume is going positive. That must be balanced by a negative quantity here, which means a net inflow, which, based on our definition of n, the n hat here, this is a outflow unit vector. So that means if this is negative, it means we have a net inflow of mass, right? So those must be balanced. All right, so the flow at the inflow, or the water, and at the outflow gasoline are assumed both uniform and incompressible, so they're incompressible flows, so it allows us to simplify the second term. Okay, so we're going to start here by just through this process we're going to consider a few different control volumes, and that's what I mean, we'll be very rigorous about this, and by considering 3 different control volumes. But one of these results is given as a general statement about, if you can make these 2 statements, we can then say that, so if we can make these 2 statements, that the inflow and outflow are uniform and incompressible, and that there's only 1 inflow and 1 outflow, it can be extended to more, but the easiest is to say for 1 inflow and 1 outflow, it must mean that the volumetric flow in and the volumetric flow out are equal. That's the statement I'm trying to say is maybe even from common sense, right? So if the fluids can't compress and they're uniform here and nothing is tricky about this, there's only 1 inflow, 1 outflow, the volumetric flow rate going in must balance the volumetric flow rate going out. Well, we're not going to just know that. Let's say we don't know that. Let's say see how we can show it for this system. So let's take the entire tank as our control volume, and that's drawn in pink here. So it's just the entire cylindrical tank, where I've gone a little bit into the inlet and outlet, where in the end our control volumes are drawn perpendicular to the flow direction. All right, and so that's important, so that this v dot n, we just pick up the entire velocity field there. Right, so v dot n, so this means that our n is parallel with v, as long as we draw our control volume or our control surface to be perpendicular to the flow. All right, so the full tank, using the control volume as the entire full tank, this is just then the time rate of change of the mass within the control volume, partial derivative here, must be balanced by the outflow minus the inflow. All right, so that comes from this term. So this is the amount of the mass flow rate leaving the control volume at the gasoline outlet, and this is the mass flow rate entering for the water, entering at the inlet. We rearrange this. We note that mass flow rates, and so, I mean, this is just making these assumptions. This is exactly what comes out from this equation. This is just the mass within the control volume. This is just m dot out minus m dot in, as long as we can make all of these assumptions. All right, so rearrange this. The time rate of change of the mass within the control volume is balanced by these 2 mass flow rates. I just moved to the other side, so now we have the mass flow rate of water written out in terms of density and volumetric flow rate minus the gasoline, right? So they've changed signs. Okay, so at this part, spoiler alert here, but QW and QG equal each other. That's what we should expect to see from our common sense. But let's just not, let's see why that's true. So let's take just the water as our control volume. So I'm going to call that CV subscripted with W for just the water. And so what we have drawn on our diagram here is the control volume with just the water component. Well, as this fills in, right, this surface is the interface between the water and gasoline goes up and up and up and up. So therefore, now we have a control volume that is changing with time. But again, as with our last sample problem, there's no relative flow across the control surface. There's no flow across the control surface, so we don't need to consider that part at all, right? So all we're going to have for this blue dashed control volume, the only flux we have is just the flux coming in, and then as long as we let this to move with the interface, there's no flow going here, right? No flow going across the control volume surface or the control surface. So that means so then our continuity equation reduces to the change in mass of water, because this control volume is only for the water. So the change in mass of the water with time is just balanced by this mass flow rate into the system, right? And here I've actually been a little bit more explicit, and we can't really, well, we know this part up here, this is going to be broken down. The total mass in the control volume is going to be the change in the, the mass of the water in that control volume plus the change in the mass of the gasoline within the system, where one's going to be positive, one's going to be negative, right? Well, here now we can actually talk about what they actually are. So the mass of the water in just the control volume with water, well, this is, comes directly from that time unsteady term in our continuity equation. This is the integral over this water control volume of just rho dV. Well, rho is constant, is an incompressible system. And then we just have integral of little volume elements over our control volume of water, right? So this is, anytime we're just integrating over little elements, right, there's no integrand in here. This just becomes the volume of the water. Well, noting this changes with time, this volume of water changes with time, but it was an easy integral at any instant in time. So our mass of water is just the density of the water times the change in volume of water with time, and that must be balanced by the mass flow rate. Right, so you can see a nice symmetry here, something coming out that's a really simple result here. So now we're getting that the densities of the water don't have any effect here, right? And that's just because we just chose our control volume to just be water. So those will cancel, and all this just says is that the volumetric flow rate entering is equal to the change in the volume of the water with time within the cylindrical tank, right? So if we allow our control volume to move upward with the water level, with the water-gasoline interface, this just tells us that the volume of water in that tank must be balanced by the flow rate, the volumetric flow rate of water entering the tank. Okay. Pretty common sense result. So we do the same thing, but now just do it for the gas only. Well, it's going to be very similar. So I'm just going to sneak the diagram back in. So now we're just taking just the gasoline. It's going to be the exact same thing we just did for the water, except here all we have is an outflow. Okay, so our this was a negative, for the inflow of water entering the control volume of water. This was a negative. Now we put in a positive because it's an outflow, and we don't have any inflow because we're allowing this control volume to follow that interface. And the same result holds true here, that we get that the change in the volume of the gasoline within the tank must be balanced by the volumetric flow rate leaving the tank. Okay? Well, from geometry, we know that the volumes of the two, the time rate of change of the volume must be balanced. So as if we're just taking the volume of the gasoline and the water, well, if the volume of the water is increasing, it's displacing a volume of gasoline. So that volume change in water must be completely balanced by the volume change in gasoline in an equal and opposite fashion. So our time rate of change of the volume of water with time must be balanced by the oppositely signed time rate of change of the volume of gas in our cylindrical tank. All right, well, now we're taking this result combined with this result and the previous result for the volume of water, the control volume of water result, so that was right here. Combine all those things, this, and this, and we get that the volumetric flow rates are equal. Okay, so just did a lot of work to show something that maybe going forward is something that we can just jump to really quickly. That we just have a single inflow and a single outflow, incompressible flow. The volumetric flow rates must be equal. Okay, so then now we're gonna go back to the full tank continuity equation, and our result at this point is just looking like this. This is where we left it the last time we saw the full tank control volume. All right, so now we have the time rate of change of the mass within the control volume, is just equal to the differences in the densities times one of the flow rates. You can choose either one because they're equal to each other, right? Well, we note that the density of gravity is just, the density of gasoline is just the density of water times the specific gravity of gasoline. Plugging everything in, being careful with our units here. All right, this is in centimeters. Everything else is in meters, or we usually use meters. So we have to make that unit change. And then also, if we want to write this in kilograms per, and we want to write this in kilograms per minute instead of kilograms per second, we just get that the total change of mass within the control volume. So the total change of mass within the tank is 1.918 kilograms per minute. All right, so the original problem statement, I think, said just determine the time rate of change of the gasoline in the tank, which you can easily do by separating this into the change in mass of water and gas. But the problem I posed here, I guess, was a little different. Just determine the time rate of change of mass in the tank, the total time rate of change of mass in the tank. So we're just going to leave it here. That the mass of the total mass within the tank is increasing with time, and that's because the water is displacing the gasoline, and water is heavier than gasoline. Water is denser. So as we get more water replacing gasoline, the total mass within the tank is increasing at a little under 2 kilograms per minute. Okay, so that one we had to be pretty careful with, and I think with a lot of the analysis at this stage seems a little bit maybe we're being really rigorous and trying to keep our analysis really careful with things that may seem intuitive. Well, at this stage, we want to make sure we're very rigorous, because later on, when things aren't so intuitive, don't come straight from intuition, we want to be able to make sure our analysis tools that are there to use. So for this last problem that focuses on unsteady conservation of mass principles, this is 5.27. And this is another one where it may seem intuitive for what the problem statement actually asks for. So we're just estimating the time required to fill a cone-shaped container, given the volumetric flow rate coming out of the supply line and some geometry of the system. Well, I'm going to make it a little bit more difficult and show why A might be easy, but B and C are not as straightforward here. So we're going to determine the time required to fill a cone-shaped container. My redrawn diagram where a supply line, where the supply volumetric flow is not just constant. So for A, we'll just say it's constant. So you have a hose that just has a constant flow with it. Perhaps maybe there is a problem with your water system such that when you turned it on at the beginning, it has 20 gallons per minute, but then it decays exponentially in time. So the longer you keep your hose on, the slower and slower the flow gets. Where A is some really small quantity here, but so it's decaying very slowly, let's say. And then C is going to be, well, let's not say that our volumetric flow isn't constant on our supply line. It also doesn't decay with time. Instead, it decays or it decreases. The flow rate actually decreases as the cone fills. So you might think maybe we're trying to fill this from the bottom instead of from the top. And so that as the height gets higher and higher, the volumetric flow rate coming in gets lower and lower as it has to push against the more weight of fluid above it. So that was my thought here is, let's make this the volumetric flow rate a function of the height of the water as well. All right, so common sense tells us that what we expect to see for this first one, A, where we have a constant volumetric flow rate, is that the so the time it takes to fill the entire tank times this constant volumetric flow rate will just give you the volume, right? So the volume that anything that any flow will fill is just always going to be the volumetric flow rate times how long it's been flowing, right? So there's a common sense here that You know the flow rate of your line, multiply it by the time, that takes away that rate part, and you're just left with the volume. So volume flow rate times time is just the volume. All right, so we can rearrange this to say that the time it takes to fill whatever we're talking about is just going to be the volume that you need to fill divided by the volumetric flow rate. Plugging things in, the volume is just pi d squared times the height over 12. So this just this comes from the volume of the cone equaling pi r squared times h over 3. So this is the area of that topmost circle, right, times the height, and then we're only getting 1/3 of that for our cone, is how you can think about this. But we've written this in terms of the diameter because that's actually what's given. So we see instead of a 3 on the bottom, we have a 12. And then just divide by the volumetric flow rate. Careful with our units again, noting that we have 231 inches cubed per gallon. And we get the time it takes to fill is going to be 12.24 minutes. All right, but again, we're going to be very careful with this. This just says, well, this is common sense. This did not come from the conservation of mass principles. It did not come from the continuity equation. This just came from maybe your common sense or your intuition about conservation of mass, not the full-out continuity equation. So instead, and I have the control volume drawn on my diagram here. It's just going to be the cone. Right, so you can see the cone, this control volume will be fixed, but we will have a net flux coming into our net flux of water coming in. Right, so it's a negative net outflow. Sorry, here's our continuity equation. Time rate of change of the mass within our control volume must be balanced by the net outflow of mass through the control surface. Well, it's incompressible, so we can pull density out, and we just get the time rate of change of the volume. So this is the time rate of change of the volume of water in our control volume, right? So I guess there is an implicit that the air here, the air inside the cone, when it's not filled with water, weighs pretty much 0, right? So the density of the air is just 0. So all we're picking up here is the total mass of the water in the system. In the control volume. Be careful with our language here. So this is just going to be the density of the water times the volume of the water, times the time rate of change of the volume of the water inside our control volume. And then we're going to, our flux term just becomes the density of the water times, so this is the mass flow rate of the water entering the system, and it's negative because it's a net inflow. Well, if we, again, noting that our densities will cancel, we get the time rate of change of the volume of the water must be balanced by the volumetric flow rate entering our control volume. Okay, same result we had last time. Again, we're still dealing with a constant control volume here. So if we separate variables and integrate here, well, it's a pretty simple one, right? d volume d time, d volume dt equals our volumetric flow rate. Well, volumetric flow rate is constant. That's a pretty easy integral, right? We're just integrating from no volume to the full volume, and integrating a constant Q from no time up to the time it takes to fill, right? So this is our initial state is no water in our cone at 0 time, and then at the T filled, so the filling time, what we're looking for is we're going to have a full volume. Pretty easy integral, and we get that equation that came out of intuition from above, right there, which then we use to solve for the filling time to be 12.24 minutes. Okay? And solve as above. Okay, for part B, it says now, what if Q is not constant, but instead a function of time, an exponentially decaying function of time for this particular instance. So here we'll do the same integral, where we'll just take dv on the left side, pull the dt to the other side, and now we're still integrating from time 0 to the filling time, where our volume goes from nothing to the full volume of the cone. Well, this side is pretty simple. This is just the volume, the full volume of the cone. But now we need to actually integrate for our Q as a function of time. Right, so we plug in, this is Q naught, this is our constant 20 here, and then here's our exponentially decaying with time part. This is just pi d squared h over 12 but over here we get a factor of minus 1 over a from the the inverse chain rule here, right? So what I always like to do is now check if I took the derivative of what I have here. Well, then we get from the chain rule we get a minus a coming out. That'll cancel the minus 1 over a that we had here, and we get back to the integrand, right? So that was a nice little check. Plugging in our bounds from 0 to t fill. Right, so it's common to just say, oh, the 0, well, that's not going to have an influence. Well, for an exponential function, it does, right? So for here, we just have e to the minus at fill minus, now if we plug in e to the 0, that's just 1. All right, so there's our bounds. We actually get a 1 there. Rearranging this a bit by pulling the negative sign over, pulling the q naught to the denominator over here, adding the 1 over here, and then, so that's just a little simplification, just doing a little algebra. Now we take the natural log to get rid of the exponential, and then to divide by 1 over a with a negative on it. That will isolate what t fill is, right? So here's our final form for t fill. We've kept everything general, so now we're just ready to just plug everything in. And when we plug everything in, I guess we have to be careful with the same things here that we're mixing feet, gallons, and inches. Right, because, well, I guess actually we just have gallons and feet here, but gallon, the conversion I have here is 231 inches cubed per gallon. So through the unit conversion we go from gallons to inches, and then up top we need to go from feet to inches to have these deal with the same units. So just be careful with that. Here again, now we get a filling time of closer to 20 minutes. So with a constant volumetric flow rate at 20 gallons per minute, right, we found it to be about a little over 12 minutes, 12.25 minutes. But if we then say that, what if our volumetric flow rate is initially 20 but then decays slowly? Well, we get a longer filling time, so that makes sense. Okay. Note that if that the volumetric flow rate, so you can now plug in the volumetric flow rate at the t filling time. So now that we know what the filling time is at about 20 minutes, plug this into our original equation for what the volumetric flow rate is. We get that the final volumetric flow rate is closer to 7.27 gallons per minute. So I said it was a slow decay, but we've gone from 20 gallons per minute down to 7.25 gallons per minute. So that's quite a drastic decay from the start to the finish, and that's why this it's close to twice as long. It's about 2/3 as long to fill this tank. Okay. So for the last one, then we said, now what if instead of decaying with time, our volumetric flow rate is still going to decrease with time, but we're going to write it in terms of the function of Q is now a function of space, or a function of H itself. So as H changes, where H is a function of time, right? What do we get the filling time here? We're again, if H is 0, we could plug H0 into here, we get just Q naught, and that Q naught is at 20 gallons per minute. So again, we're starting when there's no height in the tank, when there's no water in the cone. We still get that initial Q as 20 gallons per minute, but it will decrease as we fill up the tank. So as the cone fills, the instantaneous volume of water in the control volume is given here, right? So I've just replaced my big H and big D with little d and little h, where d and h are functions of time, all right? So at any instant in time, this is the volume of water inside the control volume. Well, just for this cone, right, this was 5 feet diameter and 5 feet high. So we also know that from similar shapes here that that the height at any instant of time, right? So the cone itself is always given such that if you go up to any height, take the diameter at that height, they're going to be equal. That's because at the full one, the full D and full H are both 5 feet. All right, so this is they're similar shapes. So since big D equals big H, little d equals little h, and therefore we can write our volume as just pi h cubed over 12 instead of pi d squared h over 12. All right. Now we go back to our equation. We say dv dt is just, we're taking the left-hand side term here, our change in volume with time is now just pi h squared over 4. We're just taking the time derivative of this, where we remember that h is a function of time. As we fill, h is getting bigger and bigger. So dv dt, d volume d time, is pi h squared over 4, right? That factor of 3 comes down and makes this a 4 instead of a 12, times dh dt. Plug that into I guess this is a direct result of the continuity equation, right? Plug that in, we get that pi h squared over 4 dh dt equals this, function of our volumetric flow rate function with h. All right. So now we're just going to separate this equation, separate variables, pull the dt over to this side, or actually we're multiplying through by dt here, and then integrating from our initial state to our final state, where the initial state is going from 0 to, time is going to go from 0 time to the filling time, and on the left-hand side we're going from no height up to the full height h. Right? So we're not dealing with the volumes anymore, we're just dealing with, dh, so we need to have our bounds go from 0 to the full h. So here we have an h squared, and then the other part, we have to separate variables, so the 1 plus h over, little h over big H comes on over. And now we just integrate this, noting that pi, 4, q naught, those are all constants, we can pull those out. And this is pretty simple because this right-hand side just goes directly to our filling time. And the left-hand side, we still see the pi over 4 q naught, but the h squared term now goes to h cubed over 3. The h cubed over h, big H term, goes to h to the 4th over 4h, 4 big H. Evaluate at our two bounds. This term becomes just 1/3 times h cubed, big H cubed. This becomes 1/4 times big H cubed. Add these together, 1/3 plus 1/4 is just 7/12. And here we're just doing some algebra. Plugging in, again, careful with units, we get that the filling time here is 21.42 minutes. Okay, so again, note, so we get an even longer filling time than before. But what's interesting here, if you actually plug in what the flow rate is at the end, when you are at the final time of filling here, well, that's going to be when our height has reached the whole total height. So q naught divided by 1 over, now instead of little h, this is now big H, because we're evaluating this at when our height at any instant in time is now the full height. We note that we've gotten half of our original flow rate, so down to 10 gallons per minute. So this took longer to fill, but we've gone from 20 gallons per minute to 10 gallons per minute. Whereas with the case B, it was we went from 20 gallons per minute down to like 7.25 gallons per minute, and it took less time, right? So there's something about the volumetric flow rate dependence on the time or space or whatever, the geometry of the system in this case, that made it so that the decaying with time, right, didn't have as much of an influence on the filling time, even though it went to a final volumetric flow rate that was much less than what we have here for case C, but the filling time was longer in this case. So, all right, so a bit interesting sample problems here, and again, the main focus here was on that unsteady part, which I feel like is often the trickiest one to think about, so we wanted to be very careful with it. We'll have another video for the next lecture supplement here dealing with more closely on that flux term part, the mass flux term.